Unsaturated compounds may be a sign of early stages of life. And so this was basically a device that was then laser welded into the Huygens probe. And then its purpose was to sample the atmosphere of Titan as the Huygens probe parachuted to the surface of Titan.
Hello and welcome to the Pitcom podcast. Today we sit down with Susan Olesik to discuss her work in enhanced fluidity liquid chromatography into carbon stationary phases. So thank you very much for joining me today, Susan. Could you please introduce yourself as well as your current position?
Sure. My name is Susan Olesik. I'm a University Distinguished Professor at Ohio State University. I'm also the Dean of Natural and Mathematical Sciences at Ohio State University.
And could you begin by providing us with an overview of your journey into the field of analytical chemistry, particularly focusing on your work in enhanced fluidity liquid chromatography and carbon stationary phases?
So I started I got my PhD in the field of mass spectrometry, and then went on to get a postdoc with Miloš Novotny and in the field of separation science with specific focus on supercritical fluid chromatography. After both of those, I decided that I was interested in going into academia and started doing research as an assistant professor in supercritical fluid chromatography combined with mass spectrometry. I became unhappy with the range of types of compounds that supercritical fluid chromatography could separate. Specifically, it was not capable of separating very polar compounds. And so my research group and I started conversations about how to have many of the capabilities of supercritical fluids, but still stay in the liquid phase. And so that's actually what enhanced fluidity liquid chromatography is. You start with conventional liquids, and to the conventional liquids you add liquefied gases. And so enhanced fluidity liquid chromatography actually gives you many of the positive attributes of supercritical fluids for chromatography, but it holds on to many of the attributes of liquids.
And what inspired you to explore this? Was there anything other than your dissatisfaction with the technologies? Did you have just a personal interest as well at that?
So no one knew, and actually many thought that what we were going to try was absolutely not going to work. And so we were chartering completely a new field. We had to define the phase conditions, how to make the mixtures so that they were one phase. We had to basically characterize all the properties of these new mixtures, which included composition and phase boundaries, what happens to the diffusion rate as a function of added liquefied CO2, what happens to the polarity of the solvents when you add liquefied CO2, and also what does the intermolecular structure of this solvent look like, which is actually really fascinating. So we did just an incredible amount of fundamental science before we could actually do any separation science at all.
Sounds like it was quite a hefty task.
It was. It was.
I can imagine.
Yes.
So speaking more on your current research activities, in your research on carbon stationary phases, what properties have you found them to exhibit, and why are they so significant to chromatographic applications?
So the reason that we started work on carbon chromatography was to define other separation media besides silica-based media. There are all sorts of reactions that happen with silica surfaces that defeat the separations. And so the thought was that if we could really control carbon surfaces well, that we would define a new type of separation science that would replace silica surfaces.
And your work with nanoscale materials for chromatographic and mass spectrometric applications it really is very fascinating. Could you discuss a particular project or discovery in this area that you personally find most exciting, or you think maybe has the most potential for other applications?
So we have discovered that if you electrospin you make nanofibers that are long fibers that are typically around 300 nanometers to 400 nanometers in diameter. If we can make a mat of those, we can actually replace a technique called matrix-assisted laser desorption ionization mass spectrometry. We can replace the matrix instead of applying a liquid matrix and then doing the mass spectrometry. We simply have a surface that absorbs the laser light, and then we get the mass spectra. So, which that technique is called SALD, surface-assisted laser desorption. Other scientists have used surface-assisted laser desorption. The reason SALD was studied is that when you use a matrix, you get all sorts of background signal in the mass spectrum from the matrix molecules, which is a real problem if you're trying to study low molecular weight compounds. If you use a surface, then the surface doesn't pollute the background and you get really clean background. What we discovered was that if you take any surface and then you spin these nanofibers onto the surface, that those nanofibers provide a surface that works really well in terms of producing signal into the mass spectrometer. Again, there's no background, and we get incredibly low detection limits by using these nanofibers. And we've actually discovered that we can lower the detection limits by making those nanofibers of polymers composites, which basically means that we're putting nanoparticles like carbon or nanoparticles of metal inside the polymer nanofibers, and that makes the ionization efficiency even higher. And so that gives us very low detection limits and high signal to noise, just spectacular signal.
And why do you think it is? What specific characteristics of nanofibers, like why do they convey this really good result and this really good success?
I think the reason that the nanofibers are providing this type of property is their high surface area. And the addition of the particles that also absorb the laser light well, I think, is helping substantially too.
Considering your commendation from NASA and your contributions to a gas chromatography column in the Cassini-Huygens probe, could you share how your research intersects with space exploration and what this collaboration means for the field of analytical chemistry?
So it was a really exciting time for my research group. We had basically an individual from NASA, and it's connected to the Pittsburgh conference. I had just come back from making a presentation at the Pittsburgh conference, and they had obviously been in the audience of one of my talks about our new carbon material. And I get this call and they say, well, we need a separation device that is capable of separating compounds, unsaturated compounds. The unsaturated compounds may be a sign of early stages of life. And so this was basically a device that was then laser welded into the Huygens probe. And then its purpose was to sample the atmosphere of Titan as the Huygens probe parachuted to the surface of Titan. And so it really shows the strong need and the applications of analytical chemistry in so many fields.
No, definitely. And for those of our listeners who may not know what Titan is, could you explain its significance to the search for life or the search for signs of life? So
Titan is Saturn's biggest moon, and at the time, we didn't know much about Titan. There was information about preliminary information from other space explorations flying by. They knew that Titan was very cold, and that it had the equivalent to Earth's mountains. It had streams, but the streams, there was no sign of water on Titan. All the streams, all the oceans equivalent, it was all hydrocarbon-based. So very, very different environment. And so the Huygens probe went to Titan to better understand what that that look like? What its moon look like, Titan?
Mm-hmm. We found something very exciting there, didn't it, as
Yes.
well? So looking to the future, where do you see the trajectory of chromatography and analytical chemistry heading, especially with the rapid advancements in, say, nanofibers or the use of nanomaterials and nanotechnology and material science?
So I think what you find in many of the happenings in separation science and in other parts of analytical chemistry is that we are continuing to advance to lower and lower detection limits, and we're starting to study markedly more complicated systems. And so the fact that we're looking at very complicated systems, and often those are biological or environmental science type applications, is driving the field of analytical chemistry also to need to perform in ways that we can't yet. But we're going to have to innovate until we can get there.
Mm-hmm, mm-hmm. And what do you consider the biggest challenges that are currently limiting those innovations or those developments?
One of the challenges that analytical chemistry has is that it works really well. Most of the devices that we produce, you put a separation device, for example. If you inject a sample in, you get signal out. It does not necessarily mean that the problem is that because it functions in some way, many individuals don't understand that it takes very skilled individuals to get the best out of that instrument. Rather, you can get a complex sample in and very little separation, and an individual may not even recognize that the instrument didn't perform well. The amount of talent that it takes to understand and allow the instrument to work really well is significant, and that's not necessarily completely.
So you've mentioned that one of the biggest challenges is perhaps this training and this kind of insight into how to properly use equipment or more experience. Do you think that this training is something that can be taught, or do you think it's purely something from experience or being in an environment with mentors that can really kind of give you that insight?
The field of separation science, actually in the US and internationally, needs more individuals who do research in academia. There's a real dearth currently of individuals like myself who do fundamental research in the field of separation science. Mm-hmm. And so the students who come out of research groups there have a much broader view of what's possible in the field of separation science. You can learn a lot by practice, but you are quite focused on what you do and what you've learned. If you actually take courses and graduate courses in the field of separation science, then you see the whole breadth of the field. And so it's markedly different. It's markedly different what you learn and what you're capable of doing. So honestly, as an example, the reason that I took the postdoc with Miloš Novotný, I was not planning on going into academia. I had many offers from industry, and after interviewing in industry and getting offers, it was clear to me that in addition to doing mass spectrometry, I was also going to be doing separation science. Mm-hmm. And I wanted to take the postdoc so that I would be much better, more broadly trained in separation science rather than having a specific company train me in that field, but simply for what they wanted to do. I wanted to know the field.
You wanted the flexibility.
I wanted the flexibility.
Yeah, that makes sense.
Yep.
Yeah. And moving kind of onto your presence here at Pittcon and your relationship with Pittcon, firstly, we'd like to wish you congratulations on being this year's award recipient of the Chromatography Forum of Delaware Valley Delnagor Award. What does this achievement mean to you personally?
So the Chromatography Forum of the Delaware Valley, that organization is very well known in the field of chromatography, in the field of separation science, for including some of the very, very best separation scientists in this country. And so to receive an award from that group is just very special. And the Delnagor Award has a very long history of excellence. So I'm just incredibly thrilled to be the recipient of that award.
Pittcon Perspectives, unforgettable Pittcon moments from the experts.
As we mark the 75th anniversary of Pittcon this year, could you share your first memory or your first experience of attending this conference and how it's impacted your view of the scientific community?
So my first experience with the Pittsburgh Conference was as a graduate student at University of Wisconsin-Madison. I think it's true today, as it was then, that academic scientists, academic analytical chemists bring their graduate students to Pittcon, and a whole collection, the whole field of analytical chemistry comes to the Pittsburgh Conference to talk and to interact with each other. So the Pittsburgh Conference is the place where we all meet. Mm-hmm. And as a young graduate student, it was just spectacular to see Pittsburgh Conference for the first time. Mm-hmm. And I, as a faculty member now, bring my students here to experience the same thing.
Oh, that's lovely. That's really lovely. And what are you most looking forward to at Pittcon 2024 in San Diego?
So far what I have discovered this time at Pittcon is again, we are seeing the very best from so many different sides of analytical chemistry. Mm-hmm. I have experienced and listened to talks in electrochemistry where individuals are looking at the extracellular space between that is in the brain and understanding how signals occur across that space and actually what's happening in that extracellular space. Mm-hmm. It's described as the big unknown for brain chemistry, and analytical chemists are doing a lot of that work. And so seeing that electrochemistry and listening to those talks is spectacular. Mm-hmm. And on the other side, we have separation science that is helping define how to basically find biomarkers that will be indicative of specific diseases. So the range of the science that happens here is just phenomenal.